Hello. The purpose of this series of lectures on simple statistics is recorded for those who are doing user study and project evaluation and so on. It's not a general nor an extensive discussion on statistics. There will be several lectures. The first one here is for the descriptive statistics. In this part, we focus on single attribute samples. So the prerequisites of this lecture assumes that you know some very basic knowledge on probability and the statistics. Presumably, you took a introduction course in your junior or even sophomore years. For an example, I would assume you know or still remember the following probability density function PDF, cumulative distribution function CDF, normal distributions, and very basic understanding of hypothesis testing, such as the p-value. We will cover hypothesis testing in great detail in later lectures. The goal of this lecture is to provide you with some basic concept and knowledge for a single attribute sample. So after you collect the data of a single attribute sample, how would you process it? So let's explain what does that mean by single attribute. It could be the scores of a problem in a test, the performance data of a class, the responses of a question in an evaluation, and so on and so forth. The data set to be used in this lecture is available, and including this slides can be downloaded from MTU's site, which will be provided in the video description section. This lecture uses Minitab for all computations. I use Minitab because it's very simple to use. You could use, of course, SAS, SPSS, and other statistics packages. All of them will provide you with the same results. And furthermore, Minitab is available for MTU students and faculties. So what you will learn includes the meaning of population and a sample. What is point estimation? Sample mean, usually I will not say sample. I would just say mean, median, mode, variance and standard deviation, skewness, and kurtosis. Then we'll move on to quartiles, outliers, and so on. And we also talk about interval estimation, confidence interval for mean and median, the central limit theorem, and the Anderson-Darling test. And finally, we approach visualization, telling you the concept of visual channels and their impact on the presentation of your graphics, the box whisker plot, and with many examples. So this lecture is part one. It includes the following descriptive statistics: population, sample, point, estimation, mean, median, mode, and so on, with many examples to illustrate the concept. First, let's talk about population. In statistics, the term population is used to describe the subject of a particular study. Population can be large, the population of the United States or any country, or small in size. For an example, a class of 20 students, and defined by any number of characteristics. Here are a few examples. Example 1, all graduate students in Department of Computer Science. It could be 30, 40, or even hundreds, or residents in Houghton County or any county. These are the populations defined by a number of characteristics: graduate student in computer science department, residents in Houghton County, or students in a particular class, women over 18 who bought vegetable at Walmart, male students in a special software development project. So a population is simply a group of subjects defined by certain characteristics. Population can be large or can be small to very small. Now, it is possible that the population is very large, making the collection of data from a population impractical or even impossible. As a result, one may only select a subset of the population, and hopefully we are able to derive the properties of the population from this subset. This subset is referred to as a sample. The procedure of selecting this sample is called sampling. Here is the diagram. Population could be very large, and sample could be small. So sample is a subset of population. A sample can be small or as large as the population. In that case, sample is equal to the population. So a random sample means the sample is drawn from the population in a random way. If we collect a sample based on certain rules, which could be biased, then your sample is not random. So normally when we collect random samples, we apply some random way to collect it. Of course, in a small study, every subject in the population would be in the sample because that is very small. Then the meaning of unbiased sample. An unbiased sample is a subset of the population using a sampling process, usually random, that does not depend on property of the subject. For an example, if you wish to know the average income of your neighborhood, then you have to randomly select household. You cannot pick those low-income household, which low income is a property of the subject. Or you select a high income. You cannot say, I will pick 50% of low income, 50% of high income, nor 30% of low income, 30% of high income, and 40% of middle income. So that means your sample cannot be selected based on the property of the subject. So basically, a random sample is a commonly used way. We will not discuss how an unbiased sample can be obtained because in our case, all students in a class are likely to be included. That is, sample is equal to the population. Anyway, let's assume that we have an unbiased sample. Why unbiased? Because if the sample is unbiased, then it's very likely that the mean, median calculated would be closely resemble the mean and median whatsoever of the population. We will return to this topic sometime later if time permits. Then one more technical definition, point estimates. A point estimate is computed using the sample data to calculate a single value. This single value is referred to as a point estimate. And this calculated single value or the point estimate serves as a best guess or best estimate of an unknown parameter of the population. For an example, the mean value of the population may not be known. and we are interested in figuring it out what the mean value of the population is. Then we select a sample and calculate the mean value of the sample. And hopefully the calculated sample mean value would closely estimate the unknown mean value of the population. The bias is the difference between the expected value of the estimator and the true but unknown population parameter being estimated. For example, we choose a random sample from which we calculate mean value, and then we don't know the true mean value of the population. And hopefully the calculated mean value, that is the point estimate of the unknown mean value, is the same. So the differences between this, the point estimate and the true value, is referred to as the bias. Well, of course, I'm not talking about in a statistical way. I'm trying to say it in an intuitive way. We will know better when we talk about the central limit theorem. So for simplicity purpose, we will not pursue the biasness issue in this lecture. Then we review some of the definitions, which you may have already learned in the statistics or even in high school course. Sample mean, usually I would just say mean. Given the sample x1 to xn, so the mean value of this sample is, we add them together, divide by the size n. The mean value is usually represented by m. The sample mean m is an unbiased estimator of the frequently unknown population mean mu. Median, you may not use median frequently, but to tell you the truth, in many situations, the use of median is more appropriate than the use of mean. So we have a sample. We sorted them from small to large, x1, x2 to xn, smallest one, the largest one. The statistical median, or just median, is defined as follows. If the number of elements or the number of data points in your sample is even, then we compute the average of the two middle one. If the sample size n is odd, then we are able to find the middle one. To the left of the middle one, we have the same number of data points as the right one. So if the sample contains extreme values, the median is more appropriate than the mean. And this is why the US Census value for income uses median rather than average. So let's take a look at this. The mean of this 4 data point is 265, which is very different from most of the data. However, the median is 25. We have 4, so we pick the middle 2 and compute the average. I usually love to tell this joke. 3 guys in a bar talking about their average annual income. One guy said 90,000. The second guy said 100,000. The third guy said it's 110,000. So the average is 100,000. The median is also 100,000. And suddenly, Bill Gates or Warren Buffett coming in, join the talk. And the 3 guys ask him, assuming that they don't know who that person is, and what is your annual income? That guy would say, well, my income is 1 million. Instantly, the average will be boosted to much larger value, but the median is still approximately 110,000. So hopefully you know when you have extreme values, the median is more appropriate. Now, remember, equal means does not imply equal medians. That is, you have two data sets. They have equal means. Would they have the same median? No. Look at this data set. 10, 20, 30, 1,000. And the second, 255, 265, and 270. Both samples have equal mean 265. But the median of this is 25. The median of this 265. Conversely, equal medians does not imply equal means. Consider two samples. This sample has median 25, but mean is 265. For this sample, the median and the mean are both 25. So suppose the sorted data set is x1, x2 to xn. If you make x1 smaller and smaller and smaller and smaller, the median is the same because it's still the average of the middle two. But the mean value, because of this smaller value of x1, will pull down below median. On the other hand, if the highest value is getting larger and larger and larger, the mean value will be pulled larger, but the median will be the same. So a caution, which will be clear later in later lectures. Parametric hypotheses testing mostly use means. We test whether two means are equal statistically, not arithmetically, while non-parametric tests use median value. You'll know that when we talk about hypothesis testing. Now, the mode or sample mode, the mode of data set is the most frequently occurring value. In a histogram of a data set, modes are the highest peaks. A data set can have no mode, one or more than one mode. If the data is numerical, that's all numbers, sort the data and identify the value that occur most frequently. If the data is categorical, sort the values by group and identify the group with the highest frequency. We will learn this very soon. So sample mode, a sample may have multiple modes. Now, look at this data set. The modes are 22, 55, 77, 99, because all of these four values appear twice. Because most property, this lecture usually does not use mode. Instead, we are more focused on the use of mean, median, and so on. Variance, the sample variance, or simply variance, S squared, measures the dispersion of the data from the mean value. It is the unbiased estimator of the unknown population variance sigma squared. Let's say we have mean value here. X1 is calculated by mean value minus this dispersion value, delta 1. It means X1 is less than the mean by this amount. X2 is larger than the mean by delta 2. X3 is larger than the mean by this value. X4 is less than the mean by this value. So these are the dispersions. Can we add them together to indicate the total dispersion? Don't do that, because we have negative value, positive value, and negative value. When you add them together, the positive values and negative value could cancel out. Even though you have very, very large dispersion, your eventual total dispersion could be 0. So how do we do that? We square them. So here, this is a data point, minus m, this is the dispersion. We square them and add them together. Now we have two slightly different formula here. But this one divide by the sum of the squares by n minus 1. This one divide the sum of square, the same sum of square by n. So what is the difference? If the mean value is calculated from the sample data, we use n minus 1. Now, if m is known, the variance here is m. This n minus 1, and n is the degree of freedom of the S square. Why? Because if m is computed from the sample, then from m and any n minus 1 xi's, one can recover the remaining missing xj. So we only need n minus 1 data value and the calculated m to recover the remaining missing xi. Let's take a look at two samples. Sample 1, sample 2, both of them has mean value 90, and their variance 2450 for the sample 1, 850 for sample 2, and the S, that is the square root of S squared, is referred to the sample standard deviation. Now look at the first sample is here. The second sample is here. Now the first sample has larger variance. It means it's spread from the minimum to the maximum. It's larger than the sample with smaller variance. Therefore, sample variance measures how the data point variate and the spreads. The sample standard deviation is simply the square root of the sample variance. In many books, statistics books or calculation algorithm book, usually you will see a formula S squared is computed by this one. We compute squares of all data points, and we compute the sum of data points and square them, divide by n, and do some other processing. And if you are writing your program, usually you may have to write your program to do some calculation. Never use this formula, because if you use that formula, you could be in big trouble. Why? Look at this one. We have 3 data points, x1, this, x2, this one plus 1, x3 is this one plus 1. As you can see, the mean, this is the mean value. And the dispersion here is 1, dispersion is 1. Therefore, it's likely that the sample variance is 1. So we add them together using exact arithmetic. So it's 2, 7 followed by 5 zeros followed by 3. And we square them, we have this value, and then divide by 3, we have this value. Now we square the first data, we square the second data, we square the third data, we add them together, we have this. Then we do this one and subtract this value, we have 2, see, 10 and 6, the difference is 2. So the variance is 1. This is the calculation by the use of exact arithmetic. However, computers, when they do floating point, computers do not have exact arithmetic. Instead, under floating point, usually you have 7 significant digits. That is, the computer can only store the 7 most significant digits. For double precision, it's probably 15. So let's assume that we do the same algorithm using 7 significant digits. So we add them together, we have this value. But in computer, we can store only 7 digits. So the 3 is gone. Now we square them. We square this value, we have this. So we still have 7 digits. And divide by 3, we still have 7 digits. Look at here. These not so significant digits are all gone. And then when we do 10 minus 6, we have this. And the variance is this large. Don't have it. In an early version of Microsoft Excel, Microsoft simply used this formula. And this is one of the issues in floating point arithmetic due to the limited number of digits a computer can store. Now let's take a look at example. In the included Excel file, that's a single data sheet. On each column, we have a heading. That column provides you the data used here. So in that data sheet, you have a column called teaching evaluation. This teaching evaluation is collected from a professor. The data is this. So look at this value. Is this professor a good one? So some calculation is needed. Mean value 3.4, median 4, and the mode is 4 or 5, and 5, and standard deviation 1.55. So this extremely high or low value can change the mean value significantly. If the data, as we mentioned, if the data set is not bell-shaped, like income, the use of median is more appropriate. Now, if you want to say, or if you intentionally or unintentionally, when you look at the data, you pick mean. Oh, this professor has a teaching evaluation of 3.41. It's just a so-so one, or just average one, right? But if you look at the median or mode, it's a completely different story. Look at the diagram again. More than 60% of students believe this professor is a very good or even excellent one. Only 20% will give this professor a very poor result. So as we mentioned over and over, very negative responses are usually from not satisfied users due to anger. I strongly encourage you to read this paper to know more, because satisfied people would not come out and say, we are content. All of those protests are formed by those people with anger, or mostly with anger. So when you look at teaching evaluation, watch out, because administrators who intentionally or unintentionally may use the mean to accuse you. Now, the same data set has a column exam score 1. This class had some unmotivated students. As a result, the mean is lower than the median, although just a little bit. The mean value is 59.29, the median 60.5, the mode is 60, the standard deviation is 16.42. So these unmotivated students score pulled down the exam score. Example 3, the programming average score shows you a totally opposite story. This class has some unmotivated student. They did not turn in their program, or they turned in a nonsense program and so on. So look at it. The mean value is 74, and the median is 80. The mode is 100. So when you look at this class in terms of programming, do you think this class is poor in programming? Definitely not, because the most occurred value is 100 full score. And even those who did not full score is still pretty high, 86. So again, very low score would pull the mean and the median toward the lower end. So when you collect your data and you try to interpret it, you cannot just simply look at the mean value, because you may misrepresent the data. The next one is skewness. Normally, statistics books do not talk about skewness, but here for completeness, we talk about skewness. Skewness is a measure of the asymmetry of a probability distribution, or the probability distribution from the data you collect. The sample skewness value can be positive, 0, or negative. A positively skewed distribution is a type of distribution in which most values are clustered around the left tail, while the right tail is longer. I will show you a diagram. On the other hand, a negatively skewed distribution would have more value clustered around the right part, and the left part is longer. The calculation of skewness is this, where x bar is mean value, sample mean, s squared is the sample variation, n is the sample size. So here is a diagram. In this distribution, it's a positively skewed, and its peak is more on the left side. So in this case, mode is the value that occurred most. Median here, mean is here. So positive skewed distribution usually have mode less than median, less than mean. And the right side is longer and thicker or thinner than the left side. So positively skewed has more value to the left. And the value on the right tail is thicker. And the value on the left side is thinner. The opposite applies to negatively skewed. More values are on the right side, so the right tail is very thin, and the left side is thicker. Usually, the mode value is larger than the mean value, is larger than the median and larger than the mean. These lower value pull the mean and median to the left. We have seen the teaching evaluation and programming average scores. Now, a perfect symmetric skewness value is 0. In this case, they are symmetric. Then mode, median, and mean are equal. Here are two very interesting examples. The skewness of a distribution tells us whether this distribution is symmetric or not. And there's no way to say when the skewness value is larger than such and such, then it's not symmetric. No. So let's take a look at this. This is almost symmetric and very close to the normal distribution. The black line here is normal distribution. And this skewness value is negative 0.058. In general, this is single value. Now, this is second distribution. It's a perfectly symmetric, and the skewness value is nearly 0. So even though you have a nearly 0 skewness value, the distribution is not normal distribution. So again, skewness value only tells us whether the distribution is symmetric or not telling you whether the distribution is normal. Now, look at this example. The skewness of this is a positively skewed. Most values are on the left side. Then we have mode 30, mean 48, approximately here, and mean 60. The skewness value 1.37, definitely it tells us it's pretty large value. It's not symmetric, and the right tail is long. This is a negatively skewed value. So the mode is here, and the median is also here, 70. The mean value is 69.57. The skew is very close, right? But this is not normal because the skewness value is still large. Absolute value is large, 1.38. It says a longer left tail. So In summary, we have the following. If your data set is negatively skewed, it usually means the peak is toward the right. On the other hand, if your data set is positively skewed, it usually means the peak is toward the left side. If the data set is nearly zero skewed, it usually means the distribution of data point is symmetric about the mean, which is equal to median, which is equal to median. Note that zero skewness does not imply the shape of the distribution being bell-shaped or M-shaped or U-shaped. It's whether it's symmetric or not. So you have to carefully construct a histogram to reveal the true shape. Example, teaching evaluation, we have this. So skewness is negative 0.57. It's negatively skewed. So most values are on the right-hand side. So as you can see, the use of mean in this case is misleading. Example 2, exam score 2. We have unmotivated students, mean value, and this difference is small, and skewness is quite small, 0.099. So this distribution is likely normal, symmetric at least. Example 3, programming average, we sorted. Mean value is this, median mode is this. And the skewness is negative 1.18, which is large in terms of absolute value. So again, in this case, the use of mean value to judge whether this student performed very good in programming is a misleading measure. Now, the last term we want to introduce to you is kurtosis. Kurtosis indicates how the tail of a distribution differ from the normal distribution. That is, the base measurement is the normal distribution. This is the way to compute kurtosis. Here, S is a sample standard deviation, X bar is a sample mean, and N has to be greater than 3. Sample kurtosis can be 0, positive, and negative. If the calculated kurtosis is 0, it means the data follows a normal distribution perfectly. Otherwise, if the calculated kurtosis value is significantly different from 0, it may indicate that the data are not normally distributed. Therefore, as we mentioned earlier, a normal distribution is a baseline for measurement. Example, if the calculated kurtosis is positive, it usually means the distribution has a sharper peak and lower, usually we said heavier tails. So positive kurtosis has a sharper peak and a heavier tail compared with normal distribution. The peak of the normal distribution is lower than this one, and the tail of the normal distribution is higher than this one. And this distribution is a commonly seen distribution we call student T distribution. On the other hand, if the kurtosis is negative, it means the distribution has a flatter peak. So this one is a beta distribution of some type. So it's a flatter peak, and its tail is higher. Usually we said lighter. Heavier would go down, lighter would float up. So here, a negative kurtosis distribution would have a flatter peak and a lighter tail. Example again, exam score 1, we have skewness 0.09, almost symmetric, kurtosis negative 0.07. So it's very small. So skewness said this distribution is likely symmetric. And the small kurtosis means the tails follows the normal distribution, and its peak is close to normal distribution. So this score distribution is likely to be normal. Now, exam score 4 data set. This, we have mean larger than median, larger than mode, and the skewness is negative 0.15, moderate, and kurtosis negative 0.96. So it means this distribution probably have a flatter peak here. Flatter peak. This is just a bump. Usually in statistics, just one data being bumped. A particular high usually does not change much. So we have a flatter peak. And we also have a lighter tail. It's going up. So could this one be normal? No, probably not. Example 3, teaching evaluation again. We saw skewness this and kurtosis negative 1.24. This is rather high. It means the right tail is very high. So this negative kurtosis shows that the evaluation score have a flatter peak and the lighter tail. Again, programming score, we have a skewness negative 1.18. We learned earlier, this is not symmetric, and the kurtosis is not so small, but not so large. So its tail, at least this part, is probably follows a normal distribution, not very closely. So a positive kurtosis shows that it has a sharper peak going up this way. Then we learn all 4, mean, 5, mean, median, mode, variance, skewness, and kurtosis. Next, we're going to talk about quartiles, outliers, and so on. We learned that the median is value at the middle. Of course, you sort your sample. So because the median is at the middle, to its left, we have 50% of data point. To its right, we also have 50% of data points. The median of the lower half is the first quartile. We call it Q1. The median of the higher 50%, we call it the third quartile, named it Q3. The median itself is the second quartile, Q2. Now, it looks kind of messy. If you sort your data, you mark your median. So to your left, you have 50%. The median of this lower left is Q1. Now, move to the right 50%, you'll find the median of this higher 50%. That median is referred to Q3. Therefore, we have Q1 less than or equal to Q2, which is less than or equal to Q3. The range is the minimum mean to the maximum max of the data set. Therefore, each of the 4 intervals from minimum to Q1, from Q1 to Q2, from Q2 to Q3, and Q3 to max contains 25% of the data point of the data set. Now, we could use a line to represent your data from minimum to maximum. So this is the 50%. Notice here, it's not divide mean to max at its middle point. No, this is the value based Q1, Q2, Q3 are the data values. So here Q2 is the median, Q1 is the median of these data, Q3 is the median of these data. Usually we also put the mean value there. The mean value could be equal to Q2 or not equal to Q2. So the interquartile range is defined to be the distance between Q1 and Q3. That is IQR, interquartile range. IQR is equal to Q3 minus Q1. So the interquartile range contains 50% of all data points. John Tukey, a very well-known statistician, suggests that a data point outside of certain range can be considered as outlier or a far out. The definition is Q1. From Q1, we multiply the IQR by a value of K. So Q1 minus K times IQR and Q3 plus K times IQR. So we have a new range going from Q1 minus K times IQR to Q3 plus K times IQR. So this range could be large or could be small, depending on the value for K. Tukey suggests that if K is 1.5, then a data point not in this range is referred to as outlier. And if you choose K to be 3, and a data point outside of this range is referred to as a far out. So in this case, we have data going from minimum to maximum. And if we choose K equals 1.5, going from here to here, data point not in this range, that's data point from minimum to here, are referred to outliers. By the same reason, if 1.5 times IQR is here to 1.5 times IQR plus Q3 is here, all data points from this point to maximum are also referred to as outliers. Why do we have outliers? An outlier point may be due to measure 0, or intentionally or unintentionally. Suppose you have a questionnaire measuring your performance from 0 to 10. Many people hate you simply give you 0. Those 0 may be outliers, although we don't know why. We have to use other questions to determine whether those zeros are intentionally that bad. By the same reason, if your performance is not so good, but at the same time, you have, say, 30% of the people give you the maximum. And if this 30% is outside of this range, so they could be outliers. So whether you're going to include outliers is your choice. Normally, we study why we have these outliers. If that is actually measurement 0, we ignore them. And if you can determine what are the reasons for you to get this outlier, study it and make your decision. Example again, program score. Yeah, we have some unmotivated students. So these are all the data, mean value and Q1, 6. The score value is 0 to 10. Median 7, Q3, 8, minimum 0, and the maximum 10. So we calculate IQR to be 2. Then we know those normal value should be in this range. That's in 3 to 11. All value less than 3 are outliers. Then we have to study why we have these outliers. Some student submitted a nonsense program. Some student did not submit. So whether you want to include this student in your calculation is your choice. Now, teaching evaluation. So the IQR, Q1 is 2, median is 4, Q3 is 5, maximum is 5. So IQR is 3. So IQR times 1.5 is 4.5. So the range goes from negative 2.5 to positive 9.5. Therefore, we don't have outliers. But if the number of beings extend to 10, definitely you will see outliers. So using 1 to 5, usually you have some very negative evaluation, but they are not outliers because those people, even though they hate you, they are not evaluating you based on their level of hateness. If you have a 10, those who really hate you or dislike you will probably give you 0. And you may have a whole lot of outliers. Now we see the program average. The program average means 74.8, median 86, mode 100. So the IQR is 97 minus 67, which is 30. So IQR times 1.5 is 45. So the range, normal value, non-outlier value is from 22 to 142. So we have some outliers here. Again, many people did not submit, and some submit some ridiculous program or nonsense program. Next time, we will move to part 2, which will be shorter. So please download the slides and review what we have discussed. Those examples are very important. Please also use the statistical package in hand and the supply data value to verify whether you get the same result. Okay, let me stop here. See you next time. Goodbye.